Hey there, how's it going? It's day two. I made it. I survived. It's day one. We're here. Another day of doing some Elm coding. Let's hop into it. So, just like last time, I have not looked at the problem yet. We've got our little template going. There's a link in the description if you guys want to just do this yourself. There's a link in the description for just this template. And it's got the dark mode and the monospace formatting. But other than that, it's just a normal LE app. So nothing too crazy. But yeah, let's take a look at day two and see what our elves are up to. Day two gift shop. You get inside and take the elevator to its only other stop, the gift shop. Thank you for visiting the North Pole, gleefully exclaims a nearby sign. You aren't sure who is even allowed to visit the North Pole, but you know you can access the lobby through here, and from there you can access the rest of the North Pole base. As you make your way through the surprisingly extensive selection, one of the clerks recognizes you and asks you for help. So it turns out one of the younger elves was playing on a gift shop computer and managed to add a whole bunch of invalid product IDs to their gift shop database. Surely it would be no trouble for you to identify the invalid product IDs for them, right? They've even checked most of the product ID ranges already. They only have a few product ID ranges, our puzzle input, that you'll need to check. For example, I'm going to copy this. The ID ranges are wrapped here for legibility. In your input, they appear on a single long line. The ranges are separated by commas. Each range gives its first ID and last ID separated by a dash, so 11, 22. Since the elf was just doing silly patterns, you can find the invalid IDs by looking for any ID which is made only of some sequence of digits repeated twice. So, 55, 5 twice, 64, 64, 64 twice, and 123, 123 would all be invalid IDs. None of the numbers have leading zeros. 0, 1, 0, 1 isn't an ID at all. 1, 0, 1, 0 is a valid ID that you would ignore. Your job is to find all of the invalid IDs that appear in the given ranges. So 11 and 22 has 2 invalid IDs. In this range, there's 1 invalid ID. Oh, got it, 10, 10. So we're going to kind of increment, turn into a string, and see if there's any repeats. There's 1 invalid ID. Wow. This is trippy. 1698522. Contains no invalid IDs. Okay. So I think there's like a brute force way to do this, and I'm trying to think ahead because I know day two is going to be like, don't go through every single thing. But let's fall into the trap. Let's see how it goes. Okay, so adding up all the invalid IDs gives us this final number. So what we're going to do is we're going to take this puzzle input. We're going to paste it into our program. I'm going to save this just in case it's not already saved. I'm going to duplicate this. Okay, so if we take our puzzle input and we compile, we're going to get our IDs. Yesterday's video, we started by breaking things up by lines. What we're going to do instead is we're going to start by breaking things up with commas. And now you're going to see all of these IDs are broken up by commas. Oh yeah, and these new lines don't exist. So I'm going to say, just for convenience, so we don't have to change the input too much, we're just going to replace all the new lines with an empty string, and that's going to get rid of, there's a new line character here that was leading to a /n over here. That was me just cleaning that up. Okay, so we've got our numbers. What I want to do is I want to turn these into like a tuple. So I'm going to say list.map to, I'll say number range, to range. So if we take a string, any of these strings, our goal is to end up with a high and a low. And I'm going to put that in a record. So I'm going to use this syntax here. And this is going to say, we're going to have kind of names for all these things. So if I've got my single item, a line or whatever, what I want to do is split that up with the dash, split that by the dash. And that's going to hopefully always give me a low and a high and nothing else. This is a bit of a pattern matching that I'm doing here. So there's going to be like a case where there's nothing. I think we want to return a nothing in that case. Otherwise, we want to return a range. And because I'm going to be using this in a few places, I'm just going to give range a name here. I'm going to give it a type alias. So now when we say range, here we just mean this record that has a low field and a high field. Cool. So if there's nothing, I guess we could just say if it doesn't match this pattern, we want nothing. Otherwise, these are still strings. What I want to do is do a maybe.map2 and run it through this range type alias. What's really cool about type aliases in Elm is you can call them like functions. You can kind of use them like constructors. So if we say maybe, if we say string.toInt, the low string, and toInt of the high string, this is like the left number and the right number, the toInt function in Elm returns a maybe because it's possible that you give it input that's not a valid number. So here, this is a valid number, but it's not a valid integer. So if I did string to int banana, that should return nothing. And so because we have these two maybes and we want to get to a maybe range, we're going to use this maybe map2 function. And it's basically just a shortcut for saying this. If the first maybe is okay, if it's in this just branch, and this is, then we're going to return range where we give it the low int and the high int. And then every other branch we want to fail. So this here, I'm just going to comment this out so that you have it for reference. It's exactly the same as us saying, sorry, maybe.map2, our constructor. And it's just a little helper function that makes it easier to write this stuff in a bit more of a concise way. But if I format this, these two lines of code are 100% the same. I just didn't want to type all this out. But now that I've typed it all out, there's really no reason to use the map2. It's only there to confuse you if you're new to Elm, I guess. But yeah, so this is really just saying, you know, turn this into a maybe, turn this into a maybe. And if they're both in the just branch, then we're good. That's a valid range. They both need to be valid integers for us to make a range. And if one of them is wrong, or if the other one's wrong, or if they're both wrong, return nothing in all those cases. And what this is going to do is this is going to help filter out invalid values. So when I compile this, you'll see that instead of all these strings, all this text, we're going to be able to turn this into a low and a high. And Elm's debug2string is sorting this alphabetically. But if I name this like A and B, you'll see that 11 and 22 is the order. We're going to leave it as low and high because we're not going to be looking at this debugging output for too long. So we're going to send this back. And then you see all these justs. In the last video, we used filter map to get rid of those. And what that does is it just gets rid of all the duds. So now we're just going to be left with a list of ranges. So by the time we get here, we've gone from string input, string, a list of strings, and now we have a list of ranges. And now that we have a list of ranges, our data is nicely parsed, and we're going to be able to rely on not finding weird stuff. So the most naive thing I can do, that I can think to do, is I can start at this number, I can turn this into a string and say, hey, is this, if I basically split this string in half, are they the same? Let me see if it's any repeats. Repeated twice. Yeah, so I don't have to worry about repeated 3 times or 4 times. That might be the day 2 or the part 2 plot twist. What I'm going to do is I'm going to basically just start at 11 and keep adding up until I get to a really big number and see if that works. There's a smarter way to do it, but I'm going to see if I can keep the code simple for now and get the right answer. I think the smarter way to do it is to kind of take half of this and try to see if there's any numbers in that range less than high and only check those. and basically increment like 1 plus 1. But I don't know. I'm talking nonsense. Let me dive into the naive implementation and see if this is going to get me the answer I need. So what I'm going to do is I'm going to take every single item in this list, and I'm going to say to invalid ID count. And so to valid ID count, I'm just going to put it here. It's going to take in one of these ranges, and it's going to return me a number saying how many invalid IDs did we find. So if I hard-coded 0 here, every single item in this list is going to be 0. But you can return anything from here. So maybe I would say, just return that number. But the idea is when we're done with this, we're going to call list.sum, and that's going to give us the total number. This is a built-in function that Elm gives us. So if we find nothing, our sum is going to be 0. If we find one invalid ID for each of our lines, we're going to get 11 because we had 11 of these IDs here. So it's up to us to return the right number here. So what I'm going to do is I am going to do some recursion, and I'm just going to be lazy. So range, I'm going to say if range.low is less than range.high, then let's make a little recursion helper. Invalid ID count help. We're going to have the count so far, and we're going to have the range, and we're going to say equals. And so here we're going to say, let's start that count at 0, and let's pass in our range. All right, so again, just to do a good job of adding annotations, make it a little bit easier to follow what the code's doing, we're going to take an account, take in a range, and return it in. This will be familiar if you've done recursion in other languages before. But what we're going to say is if the low is less than the high, we are going to kind of keep recursing. So we're going to say do count plus 1 if low is invalid ID. And then we're going to take the range and the low, and we are just going to basically just add 1 to it. So we're going to keep bumping up the low. Otherwise, we are just going to return this. 1 if low is invalid. And so 1 if low is invalid is going to be 1 if the low is an invalid ID. So if is invalid ID range.low, then we're going to give it 1, else we're going to give it 0. Another way to do this is to say, we'll do this count, we'll add 1, and then we'll just call this the new count. I think this is a little bit clearer. So let's do that. Because you notice I'm duplicating this math here. So I'm going to format this. Now, if I compile, Elm will be like, hey, you need to implement this function. So let's implement that function. I'm just going to put it here. So how do we know if an ID is invalid? An ID is invalid if you take the number, and this is a string, right? I'm going to say low string. We want it to be a string so that we can kind of take half of it and see if the left half matches the right half. So I can say left half. Let's say the string was 2. What we want to do, length 2, we'll say string dot take left, string dot length low string by 2. So this will take the left. So imagine we had like 11, or we had 100, 100, like that. What this would do is this would say, take the low string. I'm just going to do this at the pipeline style, and take this many characters from the left. So the length of this divided by 2 is 1, so it would just take 1. The length of this divided by 2 is 3, So it would just take these. So that's going to be the left half. And this is going to be the right half. So we'll take the low string and we'll drop the left amount. And so we're going to say if the left half equals the right half, then it's an invalid ID. So I'm going to compile this, and we get 8. Let's see if that's the answer. 8. Oh, sorry, that's the count. That's we don't want to return the count. We want to return basically the set of invalid IDs. So let me take a step back. We're not going to sum these. Right now what I'm doing is I'm returning how many we found. This one found 2, this found 1, 1, 1, 1, 0, 1, 1, 0. And that is the output that we're seeing here. 2, all those 1s, 0, 2 more 1s, then looks like some more 0s. Well, yeah, the rest of the ranges. So what we want to do is we want to keep the invalid IDs. We don't want to return an increment, a number. We just want to basically return those numbers as is. So instead of returning a count, you're going to return a list. And so here, this is going to be a list of integers. I'm going to rename this so that we're not calling that count anymore. This will also be a list. Invalid list. And the order doesn't seem to matter, so what I'm going to do is I'm going to say range.low, and I'm just going to put it in the front. This is the little : prepend something to a list. Otherwise, we're going to do that, and I'm going to say new list. That's what we're going to pass in here. So here, oops, got to make sure that I call the right function. And when I recurse, I need to make sure that that's named the new thing too. Oh, and this is a list. I'm getting warmer. Oh, and this returns a list. Okay, perfect. So here we have it. We've got 22, 11, 99. These are all the numbers that it found. And instead of a list.sum, I'm going to do a list.concat. That's going to flatten these lists, so it's all one continuous thing. And then, yeah, we'll do a list.sum. And then this is the number that we get, 122.777.555.4. So that seems to be right. So I'm going to save this. We're going to make sure this is called day 2 part 1. Perfect. And then I'm going to put in my puzzle input. So my input's going to be different than yours, but copy this. Let's see if I have any trouble. So I'm just going to copy this URL in case something bad happens when I run this. But it looks like we're okay. So I'm going to take that and see if that's the answer. Awesome. Okay, so the algorithm works for day 1. I'm really nervous that going through all these numbers one by one is going to be a performance problem, but we'll save the woes for part 2, and we'll see if we have to do more clever stuff. All right, the clerk quickly discovers that there are still invalid IDs in the ranges in your list. Maybe the young elf was doing other silly patterns as well. Now, an ID is invalid if it is made only of some sequence of digits repeated at least twice. Great. Okay, so 1, 2, 3, 4, 1, 2, 3, 4 is twice, but having all these, that's 3 times. Okay. I'm so glad I didn't try to hyper optimize for this weird, like, I'm going to take the thing, divide it by 2, and, you know, prevent counting or incrementing numbers, because that would have been totally in the wrong direction and would have wasted a bunch of our time. So let that be a software engineering lesson to you. Don't prematurely optimize, especially when you don't know which way the future is going to go. So we did it the naive way, it solved it, and now all we have to do is change our logic for is invalid ID. So I'm excited about that. We'll see how smart I am. We'll see if I'm able to figure it out. But I'm feeling okay. I feel like we can do this. So what I'm going to do here is I'm going to keep this output here. And this output just helps me understand how close I am to the expectations of the program. So the full answer is going to be when I concat and sum it. We will do that, but what I want to do is I'm going to duplicate this. Let me do this. I'm going to clean this up for you guys. This is our old thing. I saved it. I'm going to duplicate that tab. And then we're going to make changes here. And I just want to keep this around so that I have a link to put in the description for the video. Okay, so here we are, back to where we left off. And our code is working just fine. I'm going to collapse this. This thing thinks it crashed, but it did not. And so what we want to do now is we want to change is invalid ID to do something a little bit different. So I'm just going to rename this to part 2 before I forget. Save that, perfect. And what we're going to do is we are going to change what it means to be an invalid ID. So notice that the low string only checked the left half and the right half. What I think I can do is I can say, for example, if the low string is like 10 digits, I just need to figure out how to divide it into even parts. I can try to do that the smart way, which is saying like 6 divided by 2 and 3. Don't even try to divide it by 4. But I think I'm going to just do it the naive way, do it the dumb way, and see if we need to optimize. So rather than dividing the length by 2 every time, what I want to do is divide it by some random number. And I'm going to see if there's any libraries in the list extra package that are going to help me not have to do stuff manually. So in the Elm package ecosystem, there's a lot of cool libraries. One of them is list extra. And this is just a bunch of extra functions that might be helpful when working with lists. So you might want to take like a list of strings and like split them every, certain number. So I'm trying to see which one of these takes in a list and gives me like, split every 1, split every 2, that kind of thing. Unfold, iterate, cycle. Cycle is, it's about like looping something. Split at 3. Perfect. Okay, so what we're going to do is we're going to do something really similar to this. So we're going to split at 1, split at 2, split at 3, and we're going to keep splitting until the length, the number matches like half of the list, because that means that we've hit the half and we don't need to keep going. So I'm going to get the length of the list, or the length of that string. This is the total length. So for something like 11, this would spit out 2. And so here, this would be 11. This would spit out that. Let's use a bigger number, actually. So let's do this 1, 2, 3, 1, 2, 3, 1, 2, 3 example. This is going to spit out 9. And I'm just going to have comments here to kind of help talk through these ideas. So total length is going to be an integer. Let me just quickly annotate that. And what I want to do is I want to split, to do it, it's more than twice it shows up. Split it 1. So I think what I want to do is split it 1, split every 2, split every 3, split every 4. And so the half length is really kind of the upper bound of where I want to split. If I get to 9 or get to 4, then I don't think I want to split it anymore. It's just so weird because like this is like with a 9, it's not divisible. So I'm trying to figure out if I even want to do this. Whatever, let's do it the silly way and see how it goes. Total length divided by 2. And what I want to do is kind of get a running collection. Is invalid ID. So what do we do here? We're going to say, let's take this number. Let's turn that number into a bunch of lists of lists, I think. That'll be the way that I'm going to handle this. So I want to go list range. Start range. Let's see if this is right. Start range starting at 1, going up to the half length. Dot map. This is the n. We're going to do list dot extra. List string dot left. First, we're going to take the total, the lower string. We're going to turn this into a list. I'm going to delete her. Yeah. String dot to list. Low string. I don't know why I keep calling this string or low, but I guess we can just call this string. Num string list. And so what this is going to do is this is going to turn this into a list of characters. And I am kind of worried about the performance of this, but we'll see. Oops, sorry. I'm mindlessly doing this. This is going to split it into a list with 9 elements. So it's going to look like this. And I'm going to use the right variable name here. Okay. Let's do it there. So what we want to do is we want to, instead of saying equals equals, we're going to say take all these cuts, and I just need one of them. So if list.any, any of the ways that I slice this, whether I start cutting it into every one, or I cut it by 2 or 3 or by 4, if any of these have the same values here, basically if these lists are equal all the way through, then something went wrong. Or basically it's an invalid ID. So I'm going to say list.extra, and let's add that package. List extra. LE is amazing because it lets us install packages right here in our browser and get to use them. Split at n. So if we split it, we're going to get a list of lists. What I want to know is if they're all equal. So I'm sure list.extra has equal. Gather equals. Gather equals. I think group equal elements together will be fine. We'll just see if there's only one group. I think that'll tell us the same thing. So we're going to split at n, our original list, our number list. And then we're going to say list.extra.gather equals. This is going to return a list of basically our groups. And so these groups are just going to be more list events. So it's just going to be a list of events. It's a crazy thing. But what we're going to do is we are going to say, or sorry, this is what it's going to return. It's going to return a tuple. Now I'm going to say tuple.second. That'll give us the other groups. And I'm going to say list.isEmpty. That's going to return true if everything went into one group. So low string, I made it up. Sorry about it. Extra. Oh, I get to import a package that we just installed. List.extra. Gather equals. Argument is a list of chars. Oh, sorry, split. I think I used the wrong one. Split at int a list of A's, and it gives us 2. Oh no, this splits at 3. This doesn't split every. Split when n equals 3. Oh, split isn't what I want. Man. Group while. Select. Man. Okay, what I want to know is which one of these takes an int split at groups of. This is what I want. I want groups of 3. So groups of is the function. I just did a little bit of type-based searching. That was some groups of. Gather equals. This gives me a list of lists. Yeah, list of chars. Offsets. Okay, I want greedy groups of. This one's going to make sure to include any dangling members here. Okay, greedy groups of 1. Take my number. Gather equals. I think gather equals was what we wanted, right? Give me a list. I'm going to return a list. Oh, a list of multiple. Oh, got it. Okay, no, so it turns out I don't need to do the tuple second. I will have a list of all kinds of crazy stuff. But if there's one item in this list, that's all I care about. I thought. Okay, let's see where we're at. I'm going to do a debug log here. Oh, man. This is saying that it doesn't return anything. So if any of these... Oh, sorry. If it should be list size 1, not is empty. List.length equals 1. That means that everything went into one group. Okay, here we go. So we end up with all of these. This is kind of confusing. We use some fancy functions. Let's see if this even holds up. And if it holds up, I'll explain what I just did. But if it doesn't, there's no need to explain it because my code's not going to work. So I'm not going to waste your brain cells on a bad implementation here. And we might end up landing on a different one. So I'm going to save this. And what I'm going to do is I'm going to put in my puzzle input and see if this crashes my computer. So I've got making a lot of lists. Before I do this, I should probably test to see if we get the sum that the problem calls out. 4174 379 265. 4174 379 265. Okay, so we're good. I'm going to save this again. I'm going to paste my puzzle input. And we're going to try it. We're going to see if we did it. I'm going to copy this in case we kind of stall out. That's not a good sign. It might work still. It might just, cook my computer. I'm making a lot of intermediate lists with this strategy. I'm not too happy about that. And we are doing it for a lot of numbers. So I'm worried about that. And that is why that's why I copied this URL. So I think what I want to do, trying to think through another approach to this that's not going to create so many intermediate values in memory. No, we got our answer. Let's see if I don't have to use my brain. Easy money. All right, well, never mind. That was that. I promised I would explain. Let me cut back to the desktop here. All right, let's talk about all this weird stuff that we did, and maybe walk through some real examples. If you completely understand everything I did, feel free. It's the end of the video. Goodbye. I'll see you tomorrow. But if you want to understand what's going on, I'm going to walk you through this. We're going to do it kind of step by step, and it's going to hopefully make a lot more sense. And the first step to make this code easier to understand, cool. I'm going to clear all this, is let's start adding annotations. Anytime I see parentheses and a lambda in Elm, I always know that's a sign. I always know that this is a sign for me to make a nicely named function. Any are invalid with step size. So are invalid with step size. So we had before. I'm going to kind of make this look like a normal Elm function. It should still do the same thing. It looks like it does. And what this does is this takes in kind of like the amount to cut. And it's going to return a Boolean. It's going to say, is the length 1, is the length 0? So what we're doing at each step, if you imagine that n equals 1, and let's go to let's keep this input. What we're doing if n equals 1 is this first bit is creating groups. So the groups here, the gropus, this greedy groups of function, if we look at the docs, what it does is it takes in an integer so that we can give it our n, that's an integer, and it takes in this range and it's going to give us a list of lists. This is working on a list of numbers in the example, but in our example, it's actually a list of characters. We could simplify it. We can kind of compress the list of lists into like a list of strings if we want. But to keep it working here, what I'm going to do is I'm going to annotate this. This returns a list of characters, and every time I add an annotation, I'm going to hit compile to make sure that what I'm saying is true and I'm not taking you down a path. So if I got this wrong, Elm would let me know. It would say, hey, this thing returns a list of characters, but you said it was a list of ints. You're a liar, or your code is wrong and you didn't expect that. So if you imagine the step size is 1, what it does with a list like this is the value of groups is every single item is getting its own list. And that's where the list of lists comes from. So I'm going to make this a little bit bigger here. And so this is when n equals 1. We get this. If n equals 2, what it's doing is it's kind of just grouping these together. And so I'm just going to do this for all the examples we have. And the greedy, I remember I said I switched from groups of to greedy groups of. What groups of would have done is it would have omitted this because it wasn't length 2. We don't want that behavior. We want to know if there's a dangling thing because that means that it's not a perfect match necessarily. And I'm going to do it one more time here. And hopefully this will show you the pattern. Every time we loop through invalid step size, and we go from 1 to half length, half of 9 rounding down, this half here kind of truncates it and rounds it down. Because our length is 9, the length of this is going to be 4. And so what list.range is doing is it's creating a list that starts at 1 and goes into 4. So that's what's coming in here. And so we end up grouping these things. It might be easier to have started with a different thing, but we're actually grouping these things like this. And I'm going to just do 4 just to be thorough. And so these are the groups that we end up with. So for all of these groups, this is what we're doing. So we're kind of calling this, for this one number, for this single 1, 2, 3, 1, 2, 3, 1, 2, 3, we are creating all of these data structures. And this is why I was like, I think the computer's going to churn for a bit, because we're doing this not just for a single number, but we're doing it for everything in these ranges. Like, we are taking every number from here to here, and we're doing this over and over again. And I'm like, maybe that's not smart. But it worked, so I don't have to, it saved me some time. And what gather equals is doing is it's looping through all these lists and it is grouping them together. And so for this first one, let's say grouped lists, I guess. When we call gather equals, we can call it like this, or we can call it like this. The pipe is just syntactic sugar for passing groups into this function. What we end up with, I'm going to give it the wrong annotation so that Elm gives me the right annotation. This is a little trick. It's giving us this. And so what it's doing, this is kind of more confusing than it needs to be. But gather equals is returning what they call a non-empty list. A non-empty list is just this, where you always know you have a first element and then you might have other things. This is like a type safety thing. But you can really think of this as it takes a list and gives us a list of lists. And so for all of these values, when I pass it into kind of gather the equals, what it's doing is it's saying how many ones did I find? I think it gathers them. What I don't like about this is, oh yeah, this gathers how many groups are the same. So what we're doing here is we are saying, okay, we got this one group, and it found 2 more instances of it. So what it's doing is it's basically just kind of grouping these together. So I kind of got to hijack this function so that it could spit out something like this. So it's going to group the ones, it's going to group the twos. I'm just going to type this for brevity. But what it's doing is it's basically grouping the 3 ones together. This isn't real Elm syntax. This is just to save me a bit of time talking through this. But you can imagine that with 1, we ended up with an item that said, I got 3 1s, I got 3 2s, and I found 3 3s, because that is what we found in this list. Here, because these values are separated, these are their own unique things. So really what we found here was we found 2 groups that are 12. So I'm gonna, it's like I found 2 of these 12s. I'm using this colon just to help distinguish here. I only found 131, and I found 123. This is the 12 that we found earlier. And then I only found 1 3. But here, this is the important one. When n equals 3, what we end up with is we found 1 2 3 3 times, and we didn't find anything else. Notice the length of this is 1. So this is what I'm getting away with this weird thing. I'm kind of, in order to not make myself have to write these weird algorithms, I'm just kind of piggybacking on these things, which have very different intentions behind what they were designed for. And I'm kind of using a general thing so that I can ask, hey, if I pass you in a gathers equals, is there only one thing that gets gathered? Is there only one group of 123s? Oops, and the answer to that's yes. Sorry, I forgot a bracket here when I was explaining earlier. And so what you end up with is 1 2 3 1. This only found a single 23 1 2. And it found a single 3. So for this, as long as there's one match, we know this is an invalid ID. And so if this returns true, list.any runs on all of them. So what it ends up saying is like, this one was false because we had more than one. This one's false. This one's true. And this one's false. And because of how list.any works, if any of them are true, this whole function returns true. So I was able to kind of take advantage of some list algorithms and kind of solve it that way. But that's it. That is the whole thing. We did it. There's 2 days of Advent of Code down, 4 parts. And so yeah, I'm going to share the link with my solution. I'm excited. Drop your solution in the comments, especially if you did an Elm. There's 1000% a better way to do this than using list.extra. But hopefully me talking through it helped you understand how that weird algorithm we wrote worked and why we just barely scraped by in terms of performance. But I'll see you tomorrow, and hopefully we write something a little less crazy. Goodbye.